till now, the eigenvalue problem what we saw is something like A dot matrix A dot X equal to lambda, that is eigenvalue, into X. Now this particular problem where you multiply the vector from the right, so this X vector is called as your right eigenvector. Okay, in the matrix form, this will be a square matrix and this will be a column matrix, and we get a column matrix. So this is not the one way. There's another way also you can do. You can multiply, if you have an equation like X vector multiplied with A matrix, if it gives you lambda X. So this is also an eigenvalue problem. So this problem, when you do this problem, you call your X vector as your left eigenvector. So the left eigenvector, here what happened? So here this will be your F left eigenvector will be a kind of a will be a row matrix into a square matrix. It's a square matrix that will be again your row matrix kind of. Okay. So these are the two types of eigenvectors you can get it. One is the right eigenvector and the left eigenvector. Whatever the algorithm we saw in the earlier case, this algorithm basically for the right eigenvector. In fact, you can use the same algorithm to find out the left eigenvector also. So though we use another different methods to it, what I can say, so for example, so let us take out this one. So the left eigenvector. So let us take this problem. This is a left eigenvector. If I take a transpose on both sides, what you are going to have is X vector A matrix transpose. This will be lambda X transpose. So now this will be what? A transpose dot X transpose. That will be lambda times X transpose. Now this is nothing but a right eigenvector problem. Correct? You can always find out the this is similar to the right eigenvector problem which we are solving all along using your power method and the QR method. So now, to find out, so if you ask the question, what is my left eigenvector, is the transpose of the right eigenvector of the transpose of the matrix A. So what you have to do is, you take the transpose of the matrix A, solve for the eigenvector for the transpose of the matrix, and the eigenvector what we got, that the transpose of that vector will be your left eigenvector. So this is the way your left eigenvector can be estimated from your right eigenvector. Right, using the right eigenvector algorithm, you can find out the left eigenvector also. And now, okay, for under simple case, if your matrix A is symmetric, then your A transpose will be equal to A. So then this problem is going to be A matrix dot X transpose equal to lambda X transpose. So then what happened, particularly when the A matrix is symmetric, your left eigenvector is just the transpose of the right eigenvector, because it's the right eigenvector problem. Correct? So X transpose is a right eigenvector. The transpose of the right eigenvector is a left eigenvector. So when the matrix becomes symmetric, this problem becomes very simpler. When it is not symmetric, you have to really solve for this problem. Okay, and there's a very interesting properties, quantities we can construct from our set of right eigenvectors and the set of left eigenvectors. So for an n cross n matrix A, we are going to have n right eigenvectors, and we can also have an n left eigenvectors. So then we can construct, and what do you do? So if you remember, okay, I should have written this. So the left eigenvector problem will be something like, there is a row matrix into a square matrix, and that will give you a row matrix. Okay, so, and I'm going to construct a square matrix which I call its right Rx square matrix from the right eigenvectors, what am I going to do? I am going to place all my right eigenvectors as a columns. So all my right eigenvectors, we have n right eigenvectors. So I will place all the n right eigenvectors as a column and eventually create an n cross n matrix, and I call it as XR. So XR is a collection of all your right eigenvectors. And similarly, I can also make one XL square matrix, which is again a collection of left eigenvectors. We can see left eigenvectors are basically row vectors. So what we'll put up all the left eigenvectors of the row, and collectively we put it and call it as a left eigenvector, XL. So the XL is a square matrix which is a collection of all our left eigenvectors. So now, after one of the interesting property by why we constructing this XR and XL is, so then we can equivalently see this right eigen problem. So right eigen problem, we are taking it as a vector. Now when I take the collection of all the vectors here, how this equation will get modified. So that is interesting to see. So then A matrix dot my collection of right eigenvector matrix, that is R matrix, and you will see I am not going to do it. It's very simple. What you will see is this will be XR matrix dot diagonal matrix of lambdas, all the eigenvalues. Okay, because every x is going to have an eigenvalue. So this is what you will get. You can do it, very trivial. It is not, you can just look it and you can find out. When you put up, you will see this is what you will get it. So A dot XR will be XR into diagonal of lambda. And similarly, so we can do it for the left eigenvalue problem also. If I try to, for this problem, when I instead of one vector, if I want to give the collection of this left eigenvectors, so then this problem will be XL dot A vector will be equal to, and in this case what is going to happen is this will be a diagonal of lambdas. There's a diagonal matrix of only the eigenvalues into your XL. So you take it, for example, some component of it, and you see it by component, you will see what you are going to get is this. Okay, so we will not do this. This is pretty simple. You can just put up the component and see, are you getting back the same matrix. Okay, fine. So now, okay, let me remove this one. So let me call this as 1 and let me call this as 2. So what am I going to do? I am going to multiply XL from the left in the equation 1. So what you are going to get? So this will give me XL matrix multiplied by A matrix into XR matrix will be equal to XL matrix into XR matrix into diagonal matrix of lambdas. Okay, and similarly in this matrix I am going to multiply XR from the right. So that is, what am I going to do is, so this will be again XL matrix into A matrix dot XR matrix will be equal to, what it will be? Yeah, diagonal, we are multiplying from the right, so it will be diagonal of lambda, diagonal matrix of lambda multiplied by XL into XR. So now let me club this one. So now the left hand side is equal. So therefore this is the same. So these both should be equal. So then what it says is, so what we are getting from here is, so XL dot XR into a diagonal matrix lambda will be equal to a diagonal matrix lambda into XLXR. Now, interestingly, so what it says, so if you call this matrix as say something like, or whatever we call, let us call this matrix as, if you call this matrix as B, so then what happens? This matrix B is commuting with a diagonal matrix. So any two matrices, the matrices can commute, any matrix commuting with a diagonal matrix itself has to be diagonal, otherwise it can't commute. Okay, therefore, so if this is a diagonal matrix, this also has to be a diagonal matrix, then only they both will commute each other. Therefore, this tells you XL dot XR matrices should be diagonal. Now, interestingly, so this is a very interesting combination. So now we can choose a proper normalization and make all the diagonal elements to 1. Then what you see is all the left eigenvectors are orthogonal to the corresponding right eigenvector. So it basically forms an orthogonal vector space. Okay, so and that's interesting. So once you are given a matrix, once you are able to construct the left eigenvectors and right eigenvectors, what you are going to do is forming an orthogonal basis you are able to create from those matrices. So now the idea why we are doing these left eigenvectors and why we are taking these left eigenvectors and right eigenvectors seriously is, by doing this we can actually diagonalize a matrix given matrix A. So how we are going to diagonalize it, that we will see it later on. From here itself you can see, if I multiply from XR inverse from both the sides, what I am going to get will be a diagonal matrix, and the diagonal matrix, the diagonal elements will be nothing but my eigenvalues. Because if I multiply XR inverse from both the sides, this becomes the diagonal of lambda. So the diagonal element is going to be the eigenvalues of the matrix A, and the matrix which is diagonalizing, that XR and XR inverse, and those columns are the right eigenvectors of the matrix A. And similarly from here also, if you multiply the XL inverse from the right, so what you are going to do, so when you put XL and XL inverse, what you are going to be eventually diagonalizing the matrix A, and the diagonal elements are the eigenvalues, and the XL is already we using the XL is the matrix which diagonalizes the matrix A will be the left eigenvectors of A. So this is a one interesting property. By diagonalizing we can get the eigenvalues, all the eigenvalues as well as the eigenvectors of a matrix A. So we will see it in detail in the next lecture.